Okay, so here's, how do we get a picture? On the lower right is a picture. I know it's terribly blurry, but that's trust me, it's a color picture. On the upper left, what we do is we start with numbers. It's all numbers. It's digital data. Okay, it's just like a file on your computer. The higher the number, the brighter that area is on the surface of the Earth. We call all those millions of little boxes pixels. If you zoom in here, I know you probably can't see it in the back, but there's actually boxes of different brightnesses. Each box we call a pixel or a picture element, and each one is represented by a number. Now remember what I said before, we build these machines to detect different wavelengths of light. Most of these orbiting sensors are multispectral sensors. That means they can detect different wavelengths of light at the same time. So we actually make many different pictures, many different black and white pictures at the same instant. So in this case, we've got 3 different black and white pictures. 1, 2, 3. And they represent different wavelengths of light. This is near infrared light. This is red light, and I believe that's green light there. Might be blue, I forget. But we have those different brightness values that show how much light is reflected in each wavelength. And then in the computer program, we apply different colors to them. You add together red, green, and blue, and you get a full color picture. Now the color combination is arbitrary. I could choose to make blue represent any wavelength of light I want. There are some conventions. Often when you see these images, when you see a bright red color, that indicates the presence of vegetation. And that's a convention left over from the days of color infrared photography, aerial photography, because you can make film that's sensitive to infrared light. Instead of the red in the film being sensitive to red light that we perceive with our eyes, it's that infrared light. And it turns out vegetation reflects very strongly in that wavelength of light. So if you take a color infrared picture, a tree will appear to be actually a red color. So we take advantage of that. We build our orbiting sensors to detect these different wavelengths of light so that we can detect, for instance, the presence of vegetation, see where trees are growing and where they're not. Okay, so let's look at a few pictures here. Here's a perspective view. This is not a real picture. This is a combination of data from the Landsat satellite and a radar sensor that actually orbited on the space shuttle. What they did in a computer is they took that image and they combined it so that they told a computer program, pretend I'm flying at a certain altitude, looking at a certain direction, and we drape the imagery over the topography. So here's a canyon in front of Guadalajara, Mexico. This is the urban area right here with mountains in the background. It shows how you can combine different wavelengths of light with radar data to actually get an interesting picture. Here's another radar picture. On the left and right sides of the screen are data from one of the early Landsat satellites from a sensor we call the multispectral scanner. And it shows you the color that we see with our eyes. This is a desert landscape. This is the western desert of Egypt. If I'm doing this, you're following the shadow, obviously, not my hand. What are you pointing at? But this is just desert sand. But it turns out that the real landscape there's actually something interesting going on underneath the sand. In the center strip, this is radar data right here. Now, under certain conditions, if the sand is very dry, radar from space can actually penetrate the desert sands and then be reflected back. I should probably back up. Almost all the images we're seeing here are reflected sunlight. The source of light is the sun, right? Comes down to the Earth, it bounces back, and the satellite sees it. But in the case of radar, the satellite actually generates its own energy. It generates its own pulse of energy, and then it bounces back. And as I said, if the conditions are right, we can see underneath the sand. And you see these areas right here, these looks a little bit lighter color. Those are drainage channels. Up until about 15,000 years ago, this area had streams and trees and animals and people. But the climate changed, and now it's hyper-arid. It rains once a decade or something like that. So you can actually use, and then this bright area here indicates that the area is very rough. This is a topographic scarp that you see right here. So again, by combining data from different satellites, we can get a really whole view of what's going on down there on the surface of the Earth. Well, here you've already seen this, or a version of this. This is one of those high-resolution images. By high resolution, I mean we can see lots of detail. We can see very small things. Yes, sir? No, please. Actually, I should have said that. Please, go ahead and ask questions.
Back to that other one about the desert, where they're looking at 15,000 years ago. As a result of that, have any archaeological efforts been undertaken?
Yeah, good question. He's asking, did people use this kind of radar data as part of an archaeological expedition or to find things? Yeah, I'm aware of a couple things. One of the most famous example that hit the papers a long time ago, almost 20 years ago, was Ubar, a city in the Arabian Peninsula, which was it was a city that was written about. It was a trading center, but nobody knew exactly where it was. But some of this radar data was actually useful for finding some of the trading routes because the ground had actually been compressed a little bit. Remember what I said before, under certain conditions you can penetrate through. The conditions have to be, your ground has to be bone dry. So if you're looking at a place covered with vegetation, you're not going to be able to get much penetration, so you're not going to be able to see much. Out in this area, it's useful for seeing some large things, but not some of the small things. For instance, you're not going to be able to see something, let's say you had a room the size of this room, and maybe the sides of it were still existing. The conditions would have to be pretty good to be able to see that, because the spatial resolution doesn't allow you to see things this small with that radar data. Yeah. So, long story short, not usually, but there are some possibilities. Yeah. So this is from a satellite called QuickBird. This is one of those commercial satellites. And again, the idea was, we can use these images to do things like planning. That's where I'm from. That's the Air and Space Museum. Again, you can see cars. And if the conditions are really good, you can even see individual people. This is a skating rink, and you see the little dark splotches. Those are individual people ice skating. Now again, this is the spatial resolution. In other words, the smallest thing you can see in these images, has to be, you can definitely see cars, but it needs to be probably about the size of a person. But the reason they're visible here is because people are casting long, dark shadows on a very bright white surface. Do you see what I mean? So that the contrast is high. Usually you wouldn't be able to see individual people. All right. But these companies do have plans to launch even higher resolution satellites.
Would we see this better if these lights were out?
Would you see these better if the lights were out? I think she asked if you can see better if the lights are out, but I don't think we want to do that. Yeah. Yep.
We've had these programs before.
Sorry.
And the incandescent lights are fine.
But for your filming? Yeah. Okay. All right. Sorry. I'll do a good job of explaining. I'll watch the shadow of my hand. Okay. Now, so you just saw some images of a planned national capital. Here's another one. This is Abuja, Nigeria. Relatively new capital, carved out of the forest. Kind of like Washington, D.C., actually, although newer, of course. There's the new National Capitol building right there, and then some of the big government buildings. And again, these images are potentially useful for things like planning. Here's an example of what these high-resolution images, the history of where they come from. This is from a satellite that's actually operated by a private company. But basically what it is a former spy satellite. Former Soviet spy satellite, a very similar technology. This is an image taken of the headquarters of the Russian Pacific submarine fleet. And so here are the piers, then each of these long cylinders is a submarine. And then here's a bunch of little submarines here and here, see? And then on the upper part of the image, you see that sort of the gray area, that featureless gray area, that is ice, okay? Except you see the trail, sort of right here. That's where a submarine was leaving the port, cutting through the ice. The ice wasn't very thick, and then it submerged. This is the kind of imagery that you would have seen if you were working, in reconnaissance programs during the middle of the Cold War. Okay, this is the kind of detail. Now you see, it's a black and white image. It's not color, because for this application, we don't care what color the other guy's missiles are. We just want to know how many there are, right? And where are they, exactly? And can we get them if we have to, yeah. So what they're not interested in looking at different wavelengths of light, usually. They want that high spatial resolution. They want to see lots of detail.
Do you have ones of our subbases?
Do we have pictures of one of our subbases? Oh yeah, absolutely. Absolutely. Yes, they do. Yes, I should say actually that when we talk about satellite remote sensing, there is probably more orbiting. Well, there's just as many orbiting platforms on the reconnaissance side of the business as there are on the everything else combined, and there's probably more money on that side. So everything I'm focusing on here, there's nothing military classified about it, but it's all that side of the curtain, if you will.